Welcome back to Fundamentals of Philosophy. So this is Module 2 on reasoning, and in this module we're going to be taking a closer look at two methods of reasoning that philosophers employ to uncover and investigate the general and fundamental questions of philosophy, deductive and inductive reasoning. And this lecture is going to be focused on the specifics of the reading with an eye towards your quiz, your discussion, your written exam coming up at the end of Module 3. So we're going to be getting into the weeds. I recommend that you have the transcript in front of you when you're listening to this because we're going to be talking a lot about logic. We're going to be using syllogism, premises, conclusion, that sort of thing. And it's a lot easier to see that stuff, in my opinion, visually when it's in front of you than to just hear someone talk about it. So, and I encourage you to use the transcripts also when you're taking your quiz, when you're doing your discussions, and when you're doing your written exam. The idea is that all of that material should be embedded within this lecture. So hopefully it is. Hopefully it'll be helpful. So let's get right into it. Excuse me. Deductive reasoning. What is that? Deductive reasoning is top-down. What does that mean? It means it starts with a general principle and proceeds step by logical step to establish a specific conclusion, from the general to the specific, from the abstract to the concrete. If properly constructed, a deductive argument is necessarily true. And this is a distinction between induction and deduction. If properly constructed, a deductive argument is necessarily true. It is impossible to arrive at a false conclusion from a properly constructed deductive argument. And notice that this has to do with the structure, with the form of the argument, with the way it's built, not so much with the content. So this form-content distinction is something you're going to want to pay attention to throughout the course, because it's something that it dates back to Aristotle, and it's going to recur again and again in the discussions that we have. So, arguments can be logically analyzed into a formal structure that proceeds along lines of inference from premises to conclusions. What does that mean? Consider this classic example, which we're going to call Syllogism 1, or S1. Premise 1, all humans are mortal. Premise 2, Socrates is a human. Conclusion, therefore, Socrates is mortal. So, this syllogism and syllogism that describes the form, the premise, conclusion form, again, that goes back to Aristotle. This syllogism expresses what's known as a conditional statement. Conditional statements have the form if P, then Q, where P is the antecedent and Q is known as the consequent. So, antecedent, consequent, and if-then. So, S1, Syllogism 1, can be rephrased as, if someone is human, then they are mortal. Socrates is a human, therefore, Socrates is mortal. And you can see how the inference plays when you lay it out like that. If someone is human, then they are mortal. Socrates is a human, therefore Socrates is mortal. The structure of premise 1 establishes the conditional if-then inference from the antecedent human to the consequent mortal, right? This inferential relationship ensures that the combination of P1 and P2 must logically guarantee the truth of C. And to see why this is so, we can look at it in its formalized structure. If P, then Q. P, therefore Q. And you can see that the key to it is right there in premise 1. If P, then Q. And then P, therefore Q, premise 2 and the conclusion, are basically, it's just rephrasing what's already there in premise 1. It's restating it. So it preserves, it's what's called truth preserving. It preserves that inference that is already built into the first premise. So if P, then Q, P, and you're affirming P here. You're saying P is the case. So if P, then 2, P is the case, therefore Q, if then. So that is your inferential relationship from premises to conclusion right there. And that is your antecedent and your consequent. If P, P is the antecedent, then Q, Q is the consequent. And I'm stressing these things because they're going to come up again and again. So usually premises and conclusions, they don't arrive like neatly packaged like this into simple syllogisms that you can that have labels on them and all that. It usually takes some work. Arguments contain the structure implicitly. It's there. You got to tease it out. You got to draw it out. Look for words that indicate the presence of a conclusion, like therefore, thus, it follows that, etc. Things that indicates the speaker is queuing you up for a conclusion, that they're getting to the point. You gotta take some time, you gotta take some work to sort of tease out what conclusions you're being sold in the argument and what premises are being used to sell them. And this is very much the case in persuasive speech, like in advertising or politics. So a lot of times it's not going to be explicit, and a lot of times it's going to be intentionally embedded and buried within the language. So to make you do the work of kind of teasing it out, because if they just laid it out logically, you could see all the flaws in it, and then you wouldn't buy the product or vote for the politician. So they've got to obscure it a little bit. So logic teaches you how to pull these claims apart and see how the premises work together and whether or not they validly establish a conclusion. That's what the purpose is. So validity and soundness are two components, two properties of a deductive argument. Validity is a formal property. It refers to the structure of the argument. And here we have the form-content distinction again. It refers to the structure of the argument, not to the content. If the argument is properly formed, then it is valid, regardless of the truth of its components, right? So syllogism 1, for example, is valid because the inferential relationship between its premises is such that if P1, premise 1, and premise 2 are both true, then it is logically impossible for the conclusion to be false. That's the idea. But consider an alternative syllogism, syllogism 2. So, syllogism 2. Premise 1, all humans are immortal, live forever. Premise 2, Socrates is a human. Conclusion, therefore, Socrates is immortal. Now, syllogism 2 is deductively valid, right? It's got the right kind of if-then conditional relationship. It's well-structured, it's well-formed. The truth of C is guaranteed, the truth of the conclusion is guaranteed if premise 1 and premise 2 are both true. But the argument is not sound. And this is the difference between validity and soundness. Validity has to do with the structure. Soundness has to do with the content. It's not sound because premise 1 is not true. Unfortunately, all humans are not, in fact, immortal. They do not live forever. In fact, Socrates, they tested this, and Socrates was not, in fact, immortal. That was falsified in practice. So, not to make light of it, I suppose, but while validity is concerned only with the structure of the argument, soundness considers whether the content of the premises are actually true or false. That's the difference. To be sound, an argument must both be deductively valid and its premises must also be true. So you can't have an invalid argument that's sound. You can have an argument that is valid but unsound, but you can't have something that's sound and invalid. It's got to have both those components. Its premises have to be true, and it has to have a valid structure in order to be a sound argument. All right? Okay. So if a deductive argument is both valid and sound, then it is logically impossible for it to contain a false conclusion. You're guaranteed to have a true conclusion if you satisfy both of those conditions. And the trick there is really the true premises, because we're pretty good at logic. Logic goes back 3,000 years. It goes back to Aristotle. We've had a lot of time to work on it, and it really kicked into high gear in the 20th century with the logical empiricists, the logical atomists, all these people who mathematized logic and developed this higher order, second order predicate calculus that's incredibly sophisticated and complex and precise and powerful, that you can use to test statements and pick them apart, propositions. But the trick is, if you don't have like true premises to slot in there, then you have validity, but you don't have soundness. So, therefore, deductive validity and soundness together guarantee the certainty of a conclusion. If you have both of those things, the conclusion is certain. An argument can, however, be both invalid and unsound, and yet still contain a true conclusion. How does that work? Consider syllogism 3. All humans are immortal. Socrates is a cabbage. Therefore, Socrates is mortal. There are problems with this. It is neither valid nor sound. The conclusion cannot be validly inferred from premise 1 and premise 2. All humans are immortal plus Socrates is a cabbage does not equal Socrates is mortal. You don't have the right kind of conditional if-then relationship there. It doesn't work. So the argument is invalid. It's not formally valid. Additionally, premises 1 and 2 are both false. Humans are not typically immortal. Perhaps Highlanders and vampires, but most humans are not immortal. And Socrates, as far as we know, was not in fact a cabbage. Yet, the conclusion that Socrates is mortal is true. It just happens to be true in this case. And you can probably think of a lot of instances where people have really bad arguments, but somehow in the end stumble upon a true conclusion. The structure doesn't work. The premises don't work. It's just a matter of happenstance. It just so happens to be the case that the conclusion, completely unrelated to the value of the argument, happens to be true. It's accidentally true instead of necessarily true. So, necessity and sufficiency are going to be the next two principles that we look at. And these are extremely important, and they're also extremely tricky. They're very important properties of a well-formed argument, and we're going to encounter them again and again. They can be a little unintuitive at first, but once you get them, you kind of start seeing them everywhere. So let's go back to syllogism 1, right? All humans are mortal. Socrates is a human. Therefore, Socrates is mortal. Boom, boom, boom. In order to get to the conclusion of this argument, you need both premise 1 and premise 2. You need both of them. You can't substitute some other statement in the place of either premise and still arrive at a true conclusion. You got to have them both. Both premises are absolutely necessary in order for the argument to get off the ground. It simply doesn't work without both of them. Therefore, we say that premise 1 and premise 2 are both necessary conditions to establish the truth of the conclusion. You need both of them. Something is a necessary condition if you've got to have it. It is essential. It is necessary. It's right there in the word necessary. Further, if you have premise 1 and premise 2 together, you are guaranteed to get C. You plug those two into the equation and the conclusion pops right out. You don't need anything else. You don't need anything additional for the argument to work. You got all humans are mortal, you got Socrates as a human, and that gives you Socrates as immortal. Just mathematically that follows. Both premises together are good enough. That is, they are sufficient to establish the conclusion. So, necessity, it's necessary. Sufficient, it's necessary, you have to have it. You can't get to the conclusion without it. Sufficient, it's good enough to establish the conclusion by itself. So we describe this by saying that premise 1 and premise 2 together represent jointly sufficient conditions for establishing C, the conclusion. Jointly sufficient in this case just means both of them together are good enough to get you to the conclusion. So the premises that constitute syllogism 1 therefore represent necessary and sufficient conditions for establishing the truth of the conclusion. If you can logically prove that you have discovered the conditions that are jointly both necessary and sufficient for the truth of something, then you have solved philosophy and you can take the rest of the day off. Go have a beer, relax. You're good. That's the Holy Grail. That's what we're all sort of in the game trying to do, is because once you have that, you have said kind of all that can be said about it. Everything that is necessary and everything that is sufficient in order to make it the case. This is actually very, very hard to do, which is why we're still doing it 3,000 years later. So a condition can be necessary without being sufficient, and vice versa. So you can have one without the other in either direction. Consider the following statement. Being a reptile is a necessary condition for being a lizard. Well, this represents a necessary truth, right? It's impossible by definition to be a lizard without being a reptile. That's part of what being a lizard means, right? But watch what happens if you try to reverse the statement. Being a lizard is a necessary condition for being a reptile. That is wrong. That is not true. That is not at all true. There are tons of things that are reptiles that aren't lizards. Alligators come to mind. You guys are in Georgia. I lived in Georgia for a long time. Lots of alligators. There are lots of things that are reptiles that aren't lizards. Okay? So, being a lizard is not a necessary condition for being a reptile. Let's try the same trick again now for sufficiency. We tried it with necessity. Let's try it for sufficiency. Being a reptile is a sufficient condition for being a lizard. Well, that's also wrong. Turns out, since we know that there are reptiles that aren't lizards, we also know that it takes more than just being a reptile to make something a lizard. Being a reptile isn't sufficient to make something a lizard. Being reptilian isn't sufficient by itself to establish lizardness. But reverse the statement again. Being a lizard is a sufficient condition for being a reptile. And you have a true statement. Since you can't be a lizard without being a reptile. You can try, it doesn't work. So therefore it follows that lizardness is sufficient by itself to qualify something as reptilian. Notice another trick that's at work here. The statement, being a reptile is a necessary condition for being a lizard, and the statement, being a lizard is a sufficient condition for being a reptile, are essentially equivalent statements. They're saying the same thing. They're saying the same thing from two different directions. And this relationship, this is called logical equivalence, and it always holds. Any statement that A is necessary for B will always be logically equivalent to the statement B is sufficient for A. And if we had more time in the course, you can really, there's ways to like visualize this with set theory that are really cool, but you can see this in action. But for right now, just, again, consult the handout version of this, the transcription, and hopefully it'll seem intuitive. If not, just take my word on it. Take your time with necessity and sufficiency. They're tricky concepts. They're important, and they're pretty easy to confuse. But I mean, really, it's right there in the name. Necessary, that without which not, you got to have it. And sufficient, it's good enough by itself, guarantees the outcome. Logical fallacies. And logical fallacies are fun. We don't have a lot of time to spend with them in this course, which is unfortunate because they're everywhere and they can be pretty fun to spot. Especially in politics. They're like all over politics. So you want to be careful. You want to be able to identify and avoid logical fallacies, right? These are mistakes or errors in logical reasoning. And there's two types. There's formal and informal logical fallacies. Formal fallacies are deductively invalid, as implied by the name formal. So it has to do with the form of the argument, the structure, once again. They lack the proper formal structure to establish the necessary inferential relationship from premises to conclusion. One common example of this is affirming the consequent. And I'm going to hammer this one because it's going to come back around to us again. We're going to be seeing affirming the consequent a couple of times. Consider syllogism 4. All humans are mortal. Socrates is a mortal. Therefore, Socrates is a human. I'm going to say that again. All humans are mortal, right? Socrates is a mortal. He is amortal. He's mortal. Therefore, Socrates is a human. So on the surface, this looks a lot like syllogism 1, right? Which was valid. But it's not the same. In syllogism 1, premise 2 affirmed or agreed with the antecedent, which was human. In syllogism 4, premise 2 affirms or agrees with the consequent, which is mortal. And that breaks the validity. Affirming the antecedent, valid. Affirming the consequent, invalid. And the reason is that the conclusion doesn't follow logically or necessarily when you affirm the consequent. Socrates being mortal does not guarantee that Socrates is human. The argument mistakes a sufficient condition for a necessary condition, right? Being human may be sufficient to establish that one is mortal, right? Being human guarantees that you're mortal. You don't get out of that one. But being human is not necessary for mortality. See, there's lots of things that are mortal that aren't humans. It's almost certain that some philosopher somewhere owns a cat named Socrates, and that cat is mortal. So Socrates could, in the conclusion, therefore Socrates is a human. Just because he's mortal doesn't mean he's human. He could be a cat. Although apparently he can't be a cabbage. We established that earlier. We can formalize the fallacy of affirming the consequent like this. If P, then Q. Q, therefore P. And that's wrong. That doesn't work. And it doesn't work because there are many more things that could satisfy that conclusion. It's not guaranteed in the right sort of way. So, informal fallacies. Informal fallacies, most fallacies are informal. Informal fallacies involve the content of arguments rather than their formal structure. So we're actually dealing with the content of the argument now. One common informal fallacy is called petitio principii, which is Latin that I probably butchered, but roughly translates to begging the question. Consider this argument. We know that drugs are bad because they are illegal. Therefore, it would be bad to legalize drugs. What's wrong with that argument? There's something wrong with that. Can you find it? It's circular, right? The premise presupposes the truth of the conclusion. We know that drugs are bad because they're illegal. Therefore, it will be bad to legalize drugs. We are assuming the very thing we're trying to prove. In logical terms, we say that the argument begs the very question that is at issue. Now, the term begging the question has sort of fallen into common use as meaning the same thing as raising the question. As in, this sentence begs the question, what is the correct use of the term begging the question? Using it in this manner is an excellent way to annoy a logician. So if you ever find yourself in need of annoying a logician, just use the term begging the question when you mean raising the question. And that'll work probably 100% of the time. Unlike formal fallacies, which are always invalid, an informal fallacy may be flawed, but it's not necessarily false. In fact, assuming that a conclusion based on an informal fallacy is necessarily false is itself an informal fallacy. It's known as the fallacy fallacy. And in an earlier version of this, I had a comic that specifically was about the fallacy fallacy. Maybe I should put it back in. I don't know. In the transcript version of this, there's going to be a linked a chart that lists some common informal fallacies, ad hominem, appeal to authority, that sort of thing, naturalistic fallacy, genetic fallacy. They're all really fun. They're all really common. And again, once you start seeing them, you're going to see them everywhere. You're going to see through the matrix. Further examples, really good ones, can be found in Stephen F. Barker's article, Improving Your Thinking, in the textbook. I highly recommend you read it. So that is deductive. Now we're going to move on to inductive reasoning, which is also kind of our philosophy of science portion, because inductive reasoning is the foundation for science. So we're kind of gathering those things up together. So while deductive reasoning works from the top down, inductive reasoning works from the bottom up. What does that mean? It means it begins with particular instances and derives from them a general conclusion. One way of thinking about this is deduction moves from the abstract to the concrete. Induction moves from the concrete to the abstract. And that's why it's the foundation of science. You have to start with specific cases, with specific pieces of evidence, and then you draw general conclusions based on that. So you build scientific laws out of the patterns that you observe in nature, right? Inductive reasoning is the foundation of science because learning new facts about the world involves deriving general hypotheses from what we observe. We witness patterns in nature. We drop a glass and it falls to the ground and shatters. We drop 100 glasses in a row and they all fall to the ground. we conclude that these experiences are telling us something important about the relationship between things being dropped and things falling to the ground. There seems to be some connection there, right? Deductive reasoning makes no such appeal to experience, and this is the big difference between deduction and induction. If you understand the terms used in a logical syllogism in a deductive argument, and you slot them correctly into a valid syllogistic form, then you arrive with mathematical precision at a necessary truth. But deductive reasoning tells us nothing that was not already implied by the definitions of the terms and their logical relationship. No new information there. Deductive reasoning provides certainty, but it's a narrow certainty that is concerned only with form and indifferent to content. This type of knowledge is sometimes called a priori knowledge, from the Latin, from what is earlier. A priori is from what is earlier. Knowledge is a priori if it can be arrived at prior to and independent of experience. So it's like mathematics. You can, 2 plus 2 is 4. You don't have to go out into the world to prove that. You don't have to go out into the world to prove that a square has 4 sides. These are the sorts of things that are mathematical or geometrical truths that if you understand the definition of the terms, the conclusion follows necessarily, right? You don't have to test it against experience. But if you want to learn new facts about the content of our theories, we have to actually test them against the world. That's where induction comes in. We are forced to arrive at this knowledge inductively. That is, through experience. This type of knowledge is sometimes called a posteriori knowledge, from the Latin, from what is later, or knowledge that is arrived at after and as a result of experience. So a priori, before and independent of experience. You don't need to go to experience for it. You can figure it out. Just it's logically entailed by the meaning of the terms involved and the relationships, the logical relationships. A posteriori, you have to go to experience. You have to test your hypothesis against the world. So arrived at after and as a result of experience. But there is a trade-off. Induction can expand our knowledge of the world, but it can never provide us with certainty. If you see 1,000 white swans over the course of your life, and never a swan of any other color, you would be justified based upon the evidence in making the inductive inference that all swans are white. This argument is cogent. Cogency means that it arrives at a strong conclusion based on accurate evidence, right? But it's also false. Black swans do exist. They're just very uncommon. They're rare, but they're out there. Induction increases the level of what's called credence, or confidence that we have in the truth of a hypothesis. Regardless of how much compelling evidence we observe, there could always be yet another case that we haven't observed yet that will disprove the hypothesis. Regardless of how big our set is of cases that support the hypothesis, we could always be missing the one case that disproves it. All inductive arguments are thus open to potential revision in the light of new evidence. And this is how science progresses. This is a strength, not a weakness. Although we will definitely see some arguments to the contrary coming up in future modules. But for now, as Albert Einstein once said, no amount of experimentation can ever prove me right. A single experiment can prove me wrong. Okay, now we're going to look at some of this inductive reasoning in practice. The philosopher Carl Hempel, who's one of your readings, and this one's going to be very important for your assignments. The philosopher Carl Hempel devised a framework based upon the practices of working scientists that attempts to combine the strengths of induction and induction to provide logically valid explanations based on observed evidence. Okay? So he's trying to play on the strengths of both induction and deduction to combine them and get logically valid explanations and observed evidence of new information and logical validity. The framework he deployed is known as the deductive nomological, or DN model. And it remains probably the most influential model of scientific practice to this day. And we are not going to, in the graded portions, we're not going to get down. I'm going to walk through the deductive nomological model and the hypothetico-deductive models, but you're not going to need to know them at this level of detail. There's going to be more information here that you need, but it's going to establish the foundations for what you will need to know. The DN model, the deductive nomological model, he was terrible at naming things. The deductive nomological model has two main components. The explanandum, this is the phenomenon that requires explaining. This is the thing you're trying to explain. And the explanans, which is a set of statements that explain the phenomenon. Right? The explanans, then, the set of statements that explain the thing that you're trying to explain, can be further broken down into two components. One, initial conditions. And these are the relevant observational facts about the phenomenon, what you observe that's relevant. And two is a general law, which expresses a universal hypothesis that covers all similar observations. And this is why it's called the covering law model sometimes. The deductive nomological model is sometimes referred to as the covering law model, which is honestly a much catchier name. The DN model works by formalizing these components into a deductive argument. So you state the relevant facts, that's your initial conditions. Then you identify an applicable rule, that's your general law. And then you draw a conclusion that explains the explanandum, the thing you're trying to explain, the phenomenon in question. This formula produces an explanation that is both logically valid and subject to empirical testing. You have to have your cake and eat it too. That's the idea. The hypothetico-deductive model, which is kind of part of the deductive nomological model. And again, the naming here is... So the DN model is deductive nomological, the hypothetico-deductive is the HD model. So the DN model constructs the logical formula that connects the phenomenon, the explanandum, to its explanation, the explanans. That's the explanation. But it doesn't tell us how to derive a general law from a set of initial conditions. This leaves that part open. So you need something to fill that gap, and that's where the hypothetico-deductive model comes into play. Now, the HD model, the hypothetico-deductive, follows a clear sequence. You've got one, your initial observation. Scientists begin with the observed facts about the phenomenon that require explanation. Two, you've got hypothesis formation. Based on these observations, a hypothesis H is constructed. This is a proposed explanation that, if true, would explain the observations. Three, test implication. From the hypothesis, scientists derive specific predictions called test implications, or I, and these are concrete observable outcomes that should occur if the hypothesis is correct, right? So we should be able, if these are predictions that when we test, if these predictions come out true, that supports the hypothesis. We would expect them to be true if the hypothesis is correct. We would expect them to happen. Four is experimental testing. That's when scientists design and conduct a series of experimental tests which attempt to falsify or disconfirm the test implications. So you're trying to disprove the test implications generated by the hypothesis. You're trying to disprove I, which is generated by H. And keep the HI thing in mind. Spoiler alert. So this process is iterative, right? If the predictions fail the test, then the scientist returns to the starting point of the initial conditions and begins the process of hypothesis formation over again. And you keep doing it. This process repeats until the predictions survive the test, until you find the right predictions. At this point, the hypothesis moves one step closer towards confirmation as a covering law, explaining the initial phenomenon that started the whole investigation in the first place. So Hempel uses the case of Ignaz Semmelweis as an example in our text to demonstrate how the DN and HD models function in practice. And I'm going to attempt to sort of clarify that by showing how Semmelweis's experiments fit into the structure of these models. And again, it's probably good to have the transcript in front of you for this. And you won't need to know all of this in like specific fine detail, but it's good to have the overall structure in mind. And there are parts of it you will need to know. So the explanandum in the Semmelweis case is the large discrepancy in mortality rates from childbed fever, from puerperal, I'm sure I'm mispronouncing that, from childbed fever, between two similar maternity wards, right? So that's the explanandum. That's what he's trying to explain. That's the phenomenon under question. To establish the explanans, which is the set of explanatory statements, Semmelweis considers the set of initial conditions surrounding the spread of fever in the two wards. One variable among the set of initial conditions is the difference in the position of the mothers during delivery. Upon this basis, Semmelweis formulates a hypothesis H that the difference in birth position is influencing the mortality rate. He then formulates a test implication I that predicts that if the mothers are placed in the same birthing position, then the mortality rate should change. So you got that if-then conditional relationship again. And Semmelweis then tests this hypothesis by ensuring that the mothers in both wards are in the same birthing position and analyzes the results. And in this case, there is no significant difference. So the hypothesis is disconfirmed. Semmelweis returns back to the initial conditions and starts the process of formulating a new hypothesis all over again. So framing the test implication as a conditional if-then statement allows it to be formalized into a deductive syllogism. So this is a way to slot empirical evidence, observations, into a syllogistic logical structure, a deductively valid structure. Premise 1. If birthing positions influence mortality, then changing the position will affect mortality. Right? Premise 2. Changing the position does not affect mortality. Conclusion, therefore, birthing position does not influence mortality. This is a logically valid procedure. It's known as modus tollens, or disconfirming the consequent. Ultimately, the variable that does successfully result in changing the outcome of the test is the lack of proper sanitation routines performed by the doctors in one of the wards, in the first ward, who move directly from the morgue to the maternity ward without properly sanitizing their hands. We can state the successful test implication. Again, we could formalize it like this. Premise 1. If improper sanitation increases mortality, then improving sanitation practices will decrease mortality. Premise 2. Improving sanitation practices decreases mortality. It works. Therefore, improper sanitation increases mortality. So it is causing a change. You get different results when the doctors wash their hands. Boom. But notice that while the failed test implication ruled out birthing position, that was a valid deduction. Whereas the successful test that shows that failing to wash your hands and properly sanitize your hands increases the mortality rate, that's a clear case of affirming the consequent, right? That's if P, then Q, Q, therefore P. So it's technically invalid. And Himpel was aware. He was aware of this, that hypotheses may be conclusively refuted by a single failed test result, but they can never be decisively confirmed by any number of successful results. You're never going to get absolute certainty out of induction. Instead, successful experimental results provide corroboration for a hypothesis. A hypothesis is corroborated when it survives repeated tests where competing hypothesis has failed. So you keep testing different variables. All the other ones fail the test, but you've got one that keeps being successful again and again, no matter how many times you test. Scientists may then appeal to this hypothesis according to an inductive principle known as inference to the best explanation. Right? So you don't get certainty, but you get something like a best fit, an explanation that's the best fit amongst your available options based on the observable evidence, based on what survives the test. Now, the Semmelweis case was instrumental in the eventual development of the germ theory of contamination. This theory has held strong through countless attempts at disconfirmation. It may hold strong until the end of time, but it can never provide absolute bulletproof certainty. So it can never be conclusively proven, and we may never disprove it. It may survive forever, but we can never get there 100%. It's called asymptotic process. It approaches infinity but never actually gets there. Returning to the DN model. Okay, so we've got this. We've got the result, inference to the best explanation. We've got something that's the best fit, but it's not itself logically valid. But now we're going to return to the DN model and we're going to slot that in. Remember, we've been doing the HG model, the hypothetico-deductive model. Now we're going to take that. What we were using that for was to get the explanans that we're going to slot into the DN model, and that's where our validity is going to come from. So returning to the DN model, the deductive nomological model, the Semmelweis case provides the explanans that allows the model to explain the explanandum. Now remember, the explanans is the explanatory statements. The explanandum is the phenomenon that we want to explain, and we can do that with the DN model through a valid logical deduction. We've got the initial conditions. Doctors in the first ward did not properly disinfect their hands when moving from the morgue to the birthing ward. We have a general law. When doctors fail to properly disinfect before assisting births, the rate of childbed fever increases. And we have a conclusion. Therefore, the first ward experienced higher rates of childbed fever than the second ward. We have explained the phenomena we set out to explain. And we did so by appealing to the initial conditions and following the step-by-step process to derive a general law through testing, hypothesis testing, through testing the hypothesis, through the predictions, the test implications, the I. You got the H, which is the hypothesis. You got the test implication, which is the I. That's the prediction. You test that, and the thing that survives that has the most robust survival rate across multiple tests is the best fit, is the best explanation. And then you slot this into the DN model, and you have something like a valid explanation. Even though the inductive content of the argument, what is sometimes called the context of discovery, can never be absolutely certain, the deductive form of the argument, the context of justification, can ensure that the explanation is logically valid. There's your form-content distinction once again. So, based upon his findings, Semmelweis became a relentless advocate of the importance of antiseptic hand washing to prevent the spread of contamination, which seems uncontroversial to us now, but was it was a radical idea in the mid 19th century, in the sort of 1850s or so when he proposed it. He did not, however, propose a robust mechanism for transmission beyond speculating that some sort of invisible cadaverous particles were being carried by the doctors from the morgue to the maternity ward. His work was primarily experimental rather than theoretical. At the time, the dominant explanation for disease transmission was what was called the miasma theory, which suggested that contagion was spread through bad air or noxious vapors. They didn't know about germs. It's a relatively new thing. So against this background, the suggestion that it was the doctors themselves who were transmitting contagious materials through lack of proper sanitation habits, it faced intense institutional resistance and even outrage from the medical community. So and again, we're in the mid-19th century here, 1850s or so. Doctors were at this time generally considered to be, and considered themselves to be, high-status, educated gentlemen. Hand washing was something associated with the lower laboring classes, right? Doctors, they already had clean hands. They were the right sort of person to have clean hands. It was the poor laboring working classes who had dirty hands, especially the midwives. And the doctors did not take very kindly to being put in the same class as lower class laborers and midwives. So to suggest that the hands of doctors were as unclean as those of the laboring classes was viewed as an attack on the prestige and the dignity of the profession. Worse, it seemed to be suggesting that doctors were knowingly placing their patients in danger, that they were the ones, their practices were, their lack of cleanliness was killing their patients, which was true. Semmelweis was frustrated by this institutional resistance to his empirical findings. I mean, it was cut and dried for him. He was testing the hypothesis. It was again and again, he was coming to the same conclusion. He was seeing the same results, but he could not get people to look at that because it challenged the dominant narrative they had, the way they thought about themselves and their place within this culture, their status. There's an old cliche that it's hard to convince someone of something if their paycheck depends on them not being convinced by it, not understanding it. So Semmelweis's advocacy becomes increasingly combative. He gets angry, he gets accusatory, he's emotionally charged, he's raging against the machine here. And as a result, he gets dismissed from his professional role within the hospital. And eventually, he is ultimately committed forcefully and against his will to an asylum, where he suffers systematic physical abuse for years, culminating, ironically, in an infected hand wound that becomes septic, leading to his death very soon, very shortly thereafter, from the very form of contagion, from the very form of contamination that he had spent decades attempting to diagnose and treat. That is the tragedy of the Semmelweis case. And in a few short years after Semmelweis's death, this was actually happening around the same time, Louis Pasteur and Robert Koch were developing the germ theory of contamination. It was actually happening independently. And that would eventually displace the miasma theory and vindicate Semmelweis's intuitions regarding the relationship between sanitation and disease transmission. So that work was out there, it was already happening. And while they had Semmelweis locked up and were torturing him and eventually, there's some disagreement in the scholarship amongst historians whether it was he obtained the wound as a result of the abuse that he suffered, or if he had perhaps did it, if it was maybe self-inflicted, that essentially he decided to ultimately prove his case by using himself as the final demonstration, the final test of his hypothesis. Regardless, the Semmelweis case represents yet another tragic example of a revolutionary thinker who faced persecution from the authorities of his time for the crime of coming up with an inconveniently good idea. And that's probably a good place to end. Hopefully this has been useful or entertaining, maybe all of the above. If you are following along with the transcript, which you should be, there is going to be an existential comic at the end of this on the philosophy of magic. Again, I recommend take a look at that. And otherwise, hope you enjoy this. See you soon.